Section's entitled Scheduling. Use label selectors to schedule pods. Also, you may have noticed the volume is a little bit louder. That's because I figured out how to adjust my microphone volume after all. Okay, so in this video we are going to explore scheduling of pods, which amounts to a process by which newly created pods, they have to be assigned at some point or bound to a node to run. And the scheduler process monitors new pods coming online and figures out which node to place them on. Now, out of the box, Kubernetes ships with a scheduler called Kube Scheduler. It's currently running in our control plane, and but you could actually create other schedulers and run them alongside of Kube Scheduler. So there's not only one. So in general, the process by which a scheduler works is it first goes through and determines which nodes it possibly could run on the pod. Those are called the feasible nodes that the pods can run on. And then based on that, it has some internal scoring process by which it ranks the nodes and then eventually picks the right node for the pod to run on, and then it hands it back, right? So I think that process is called binding. So throughout the rest of this video, all the stuff we're going to look at all only pertains to the scheduling process, meaning up until the point where the node picks it up. Once the node is executing the pod, all the configuration we're going to touch here does not have any relevance on what's actually running. So if after it's running, the scheduler would not normally schedule something in the future, it does not mean that it's going to remove a process that's already running. Later video we'll talk about process sub-mechanisms that allow for that, but the stuff we're talking about in this video does not. Okay, so we mentioned briefly that there's a concept of a custom scheduler. So there's an article in Kubernetes that talks about how to configure multiple schedulers, and they give you a sample code for a scheduler, and then they walk you through the process of installing it. It's kind of lengthy, and decided not to go through it myself. So instead, I just kind of summarizing it. The process generally involves you install a new scheduler using a deployment, right? There's some code that's packaged up in a container. You write your own deployment. You deploy it. As part of that configuration, the cluster itself, there's a cluster-wide name called the scheduler's name, right? And that name has to be unique cluster-wide. So that's part of the way the scheduler works. It advertises a name, okay? And by the way, the name of the one that ships with Kubernetes, the name that's given is default -scheduler. We'll see that when we look shortly. We'll actually examine that. We haven't been specifying that, so but it gets actually, well, anyway, that's what there is a name. I guess I kind of led to the next thing. So the way that if you're creating a new pod, if you want to pick which scheduler is going to schedule this pod, you actually can provide under the spec a scheduler name with that string. So if you say scheduler name default scheduler, it's going to behave just like normal. If you have scheduler name my other scheduler, it would then pick anything that, any scheduler that you installed with that unique global name. Okay. The next section here we're going to talk about, interesting, is how do we not use the scheduler for assigning pods to nodes? And it's actually one of the questions or one of the outlined items in the curricula for the course. So anyway, luckily I found this. So the way you do this is, if you think about it, right, the scheduler's job is to assign a node. So the way you avoid using a scheduler is just assign the node yourself. In this case, you specify it's super easy. You just specify node name as one of the first, under the spec, and you give a valid node name to the right, so it's a key value pair. And that's it. And once that value is there, the schedulers will not pick it up because there's already a node name assigned, in which case it gets assigned to that node and you're done, right? So what I want to do here is we're going to look at some code first. Now, I'm going to run this twice. I'm going to run it once where I do not specify a node name, right? And we're just going to observe the scheduling process as it normally operates. And then we're going to use node name and then watch the scheduling process then, okay? So, control, let's see, Helm, let's see, what am I doing here? Helm, ls, uninstall dev. I had something installed right before this, so we'll get all. The pod's still running, which I have to wait for this. I'm going to pause the video until this pod stops. So you can see that I've got a clean, nothing running again. So I'm going to do helm install dev node name. So this is actually sort of the node name. So here we go. So kube control get all. So kube control. Okay, so I see it's running. So I'm going to describe pod example. I'm going to observe a couple things. One is, let's see, it's running. Everything's good. So I think the most interesting thing here, I guess, is the first thing that happens is you can see from default scheduler. So that's where the default scheduler comes into play, and it tells you which scheduler did it, and it successfully assigned it to a node. Right now, another thing we can look at too. Let's see if I can find it. So kube control. There's a little bit of an experiment here. Oh, here it is, right here. I was looking. I wish the events would show at the bottom, but I guess other things have happened. Anyway, the newest last seen 12 minutes. What this 12M is, but oh, whatever. This right here looks like the scheduling process, and you can see that there's my pod example successfully. Right, so you can see that the scheduling process outside of looking at the pod itself. Okay, and one other thing I want to look at here is kube control get pod example. I wanted to see that node entry, see if I can get to here. So metadata spec node name. So here's that node name right here. So you can see that even though I didn't specify node name, now the spec actually has a node name on it, and that's because the scheduler put it there, right? So we could, in theory, if I was to do this, I think we'll do it. I'm going to copy this, right? And so now I'm going to do helm uninstall dev. Okay, and then I'm going to edit spec here. I'm going to put in node name directly. So, okay, under containers. So it's a top level under spec, right? So I'm just specifying the node name directly. And now, puddle get all. I'm probably going to have to pause the video again. Okay, I'm going to pause the video again. Wait for this old pod to terminate. Okay, I'm back. So I'm now going to do helm install node name install dev node name, and we're just going to observe what this pod looks like now that we've specified node name. Does it, how does it work? So kube control get all. So it's running. Okay. Kube control describe pod example. Right. So the important thing to notice here is that you'll notice that there is no message about it being scheduled. Right. So it didn't go through the scheduler. And if I look through the events too, if I do kube control events, and I grep out schedule, so there's an early scheduled. So if I go this grep, let's see if this actually. Okay, all right. So if you look at this, I had done once. Okay, so I did one about 16 minutes ago, earlier this morning, and then the one I did the first time, you can see it's here, right? But you don't see a third one, which was maybe about 30 seconds ago. So you can see that there was no scheduler. Scheduler did not actually do anything with this pod. Okay, so that's all I really wanted to see there. So helm uninstall dev. Now, one interesting observation that threw me, I had to record this video a second time because I got confused. If you give an invalid node name here, right, what happens is the pod will show up, and then very quickly the pod will just disappear. You won't see it. And I was expecting it to stay in an unscheduled status, right? But that's actually not true because you've told what node name it is. The scheduler is not picking it up. So this node gets sent to that node to run. It doesn't run because there is no node by that name, and it just disappears out of the system. Whereas if you have other problems with scheduling, like you don't specify node name, you've done something so the scheduler can't do it, the pod will still stay there in unscheduled status. So just be warned, if you said node name to something that's not valid, it will basically disappear on you, and you lose there's like no logs, it just disappears. Okay, I'm gonna leave this one configured. Right, I'm gonna actually delete this so that, well, no, I think I'll leave it in there. Okay, I'll leave it in. Okay. Let's go back to the video recording. So that was how to bypass the scheduler. The next one, another mechanism to select nodes is with something called a node selector. So what I want to do here was, let's get nodes here. So I have two nodes, right? So I'm going to describe one of them. I didn't mean to do get. I meant to do describe. Okay. So if you look at these nodes, I want to look at one thing in particular. See all these labels here? So these labels were when we installed Kubernetes. These nodes got assigned these labels as part of the core configuration. I didn't do them separately, right? And if you look at them, they all seem to make sense. They're all about the operating system, maybe what network they're running on, things like that. And of particular importance I wanted to pay attention to was this topology entry. There's this, and this is in World of Amazon, this is the availability zone, and we're going to use that throughout this video. It's this label, topology EBS CSI AWS.com/zone. Now, I could have also used probably this one here, because it mentions, this seems to be more of a generalized concept, the failure domain. And that has, conceptually, maybe that's a high level abstraction of what an availability zone is, right? It's a zone where you have a high likelihood of things failing to get, well, not high likelihood, but possible likelihood, right? So, but just for ease of this video, I'm going to stick with just using the more concrete topology entry here. I could have probably used the other one too, though. Okay, so the point here is there's a bunch of labels, and we can use these labels. So that's what the whole point of this exercise here is. We can use this label to then decide which node you're going to run on by saying, I want this label to equal this. Now, I think the easiest way to see this is to look at it. Now, I think about it, so this is 1A. I'm curious to see, okay, so, okay, I have one of the nodes running in 1A. Kube control, get nodes. Let's see what the other one's running in. I'm hoping it's in a different, should be in a different zone. This one is in 1B. Yeah. Okay. So I have two nodes in two different Amazon availability zones, and let's say I want to target this to one of the two zones, right? So clear, and I go into code. Node selector. Okay. Okay, so let's look at this example here. Now, if you recall from the last video where we're doing storage, we actually created a elastic EBS volume in a particular zone, right? And in doing so, we needed to really make sure that this pod ran in the same zone as the EBS volume, right? And before we did it, because we were running just one node, we kind of cheated the system by just looking at that node, finding out what zone it was, and then manually created the volume in the same zone. In this case, we're going to validate that we got a volume in a certain, in this case, US East 1. And you can see there's this entry here, node selector, and then I give a key value pair. And what it's going to do is, when this pod gets scheduled, it's only going to schedule on those nodes where it can find matching labels. In this case, it will not schedule on the one in A, only on B. Now, in order to run this, I need to make sure that I actually have an EBS volume, because I may have cleaned up after myself. I guess I could do this. I guess I can do this quickly, I think. If not, I'll pause the video. So what I'm doing is I'm going here to make sure that I manually create a volume. What are these volumes at? Volumes. I have a couple floating around. There's one right here that's in use. Available. So let me look at this one here. So I want to make sure I use this one. It may or may not be the one I have here. Ends in 9F. Ah, that is it. Okay, so it's still floating there, available. Okay, so what I want to do now is I want to run this, and it should basically, because the volume is in, oh wait, I should make sure the volume is in 1B. It is in B. Okay, so that's good. So if I run this, the volume's in B, I made it run on B, everything should work fine. If I switch this to A, this probably won't work so well, because this volume, this pod would be scheduled to A, but then it won't be able to see this volume, and it would probably fail. And I'm tempted to try it, but I don't know. In the interest of time, I'm not going to do it. But okay, so if I do kube control, no, helm, install dev node selector. So okay, so kube control get. I think people say kubectl, but I think it's kubectl easier to me, to be honest. It's running. Let's look at what node it. Kubectl describe pod example. So it got scheduled to the one with an IP address of 15, right? So what I should do is I'm going to copy this. That's the node name. And then kubectl describe node this. And then I should indeed see this is the one that's with a label of B, and it is, right? So I was not expecting to see A, right? Because the scheduler used the node selector to then decide which node to use. Okay, so I think that's it for that. Let's see what else we have here. Hang on. Okay, there's a couple other things that I'm going to slip in here, just some couple notes. So, and I'm not sure if it's important for the exam, but there is a concept of, so this is a process by where we're using labels to decide which nodes things land on. And in this case, it wasn't for security reasons, it was because we had some resource constraints, right? So there are concepts where you maybe have a concept of more secure nodes than others, and you want to control, oh, I want this pod to run on the secure node, not on the insecure node. And the problem with that is that because it's security related, you might be concerned that apparently Kubelet itself has the ability to write into API server, right, as part of its normal processes. And without anything special in place, you can imagine that Kubelet, if someone hacks one of your nodes, right, gets a hold of the Kubelet process, and maybe it's an insecure node, right, maybe a test, like a dev node or something. And what, in theory, it can do is it can actually, if it gains access to the API server, it can then schedule maybe secure services into itself, secure pods, things that maybe it shouldn't have access to. And then you just, now you've got some rogue process that has too much access, right? So the idea here is you can actually, there's a mechanism where if you use labels on your nodes, right, that start off with node restriction kubernetes-io, right, and then you have to enable this thing called the node emission controller on your cluster, right? That basically what that does now is it changes the way Kubelet has access, and Kubelet will no longer be able to touch this label. They can't go there and monkey around with this label. Like, they couldn't assign themselves their node itself this label, and thus pick up or any label that starts with this prefix, and it wouldn't be able to then take on secured pods themselves. Now it turns out that to enable and disable this, there's some flags that are that when you start up Kube API server, and of course we're using EKS where we didn't actually run our own command line for API server. And the good news is that for EKS, this is actually included in the pre-compiled list of emission controllers that are already installed. And apparently, even if it didn't, there's something called a dynamic emission control, where you can basically use webhooks with EKS to expand on how it does, how the Kube API server works. Okay. Long story short, there is a concept of labels that are special in the sense that they can be set so that you can ensure that pods only get scheduled to the right nodes and not to these hacked nodes. Okay. Kind of rambly there, but okay, enough about that. Okay, so far outside that sidebar, we were talking about node selector as kind of an easy button way to select nodes, right? But there, part of the problem was that it's very kind of black or white. Does it have a label or does it not have a label, right? And so there's another way of doing it called affinities and anti-infinities. affinities, which give you a lot more flexibility in how to control the scheduling process. So the reasons why you might use it, obviously I just said, is it's more expressive. You can do a lot more things with it. You can create, instead of just hard, like previously, right, it's either labels there or it's not there. So that's it, black or white. You can create soft preferences, which is try to, you can say, oh, try to put it in here, but if it doesn't work, do something else. And then more interesting is you could also create rules that not only look at the nodes labels, but it can also look at other pods, right, and where they're running, and use their labels to then drive your decision, right? So that's where you want to do things like, you might want to co-locate a bunch of pods all on the same host, for example, right, or on the same node. Right? So that's again that really more to do with where the other pod's running at, right? So okay, so we're going to sort of break this down into pieces. Okay, and let me pause for a minute just to regroup for a second. Okay, so the first thing we're going to talk about is node affinity, and looking ahead, we'll look at something called pod affinity. And the names are pretty expressive, right? Node affinity has to do with making rules around what node you want to be on based on the node, and then pod affinity is what nodes you're going to be on based on maybe pod information. So it's very similar. Node affinity is similar to node selector, right? Basically allows you to decide which nodes are based on labels of the node itself. Okay, and now there's two different kinds of node affinity, rules that you can put in. One is called, it's got this kind of unwieldy name, required during scheduling, ignored during execution, and another one is preferred during scheduling, ignored during execution. And apparently they're looking forward to the future where they can now use the same process to deal with currently executing pods, but that doesn't exist today. So I think they created the name anticipating that we'll eventually add some features in the future where you can use these mechanisms, same processes, to control what's actually running at execution time, right? But so everything, like I said earlier, everything in this video here is going to be only about scheduling, and then this name is somewhat descriptive of that. The big difference here, one is required and one is preferred. And as we indicated earlier, the required one is basically a hard scheduler. Like, it will not schedule it unless you meet the rules. And preferred is like, well, try that first, and then, or actually what it really does is if you think about the process, the preferred process will first let, pretty much any node through it, right? And then it'll basically give scoring values, right? And give higher weights to things that are preferred, so that when the second part of the process of scheduling nodes where it actually uses scoring, those nodes pop up to the top, and that's why you get onto that node, right? So this top one is more like part of the first step, which is just determining which nodes are part of the, and I'm forgetting the word, I should look it up here again. The right word is, it is part of the feasible nodes. So the required step is really about setting what is feasible, and the preferred is about, let me get back to where I was at here just a minute. And preferred during scheduling is more about setting the score just among feasible nodes. Now, I think just for simplicity, in this video, I'm only going to deal with the required, because there's almost too much to cover. But you look at the docs, you can see how preferred comes into play. So I'm going to look at this one called node affinity. So let's look at it. Okay. Node affinity. And to be honest, this stuff gets a little bit complicated. At least in my mind, I started getting myself confused. So I'm trying to keep it simple here. Okay, so the rest of this is exactly the same as my earlier example, right? I've got my pod. I'm doing that volume. I want to make sure this is on on US East 1 because I know that this EBS volume is there, right? Before I used, what did I use before? I used node, not node name, but I used node, this is good practice for me. I used node selector, right? Now, instead, I'm using affinity. And if you look at the code here, it's a lot more complicated. But actually, in this case, it's going to accomplish the same thing as what I did earlier, right? So I'm going to just kind of read through here, right? So you have to use affinity to trigger that you're using affinity rules. Then you have to say that I'm using a node affinity as opposed to a pod affinity, so that all makes sense. And then we talked about this two flavors of node affinity. There's required during or preferred during, so using the required one, so then you're already now 3 indents in. And then the rest of this is, I'm just following kind of a boilerplate. So node selector terms makes sense. And then you have an array of things here. And you have, in this case, you have something called match expressions. And then under there's an array within array, right? So let's look at the bottommost one and see if it makes sure this makes sense. This expression says, look at the key. This is all about labels. So look at this topology zone and make sure that this value, US East 1, is in that one, right? So what this will do is this will only select nodes that US East 1 is one of the choices in that label. So like for example, the one that has US East 1B, that the actual label is in that list, and the 1A is not in that list. So this will basically only make the one that's in availability zone B feasible. The one in A will not be feasible. Okay, so that's how you read this. Now what's a little bit confusing here is, and see if I get this right, if you have under a match expression multiple keys, right? So if you have key 1, key 2, key 3, these are all ANDed together at this level. So in which case all the keys have to exist. And that would be kind of like just your node selector where you specify multiple labels, right? Now the outermost array, the match expressions, if you have multiple match expressions, then those are ORed. Means if any of them succeed, then it matches, right? So inner one is and that's what makes it behave like a node selector. The outer one is the new thing where you can actually have multiple match expressions, and if any one of them are successful, then it will schedule it on that node. Okay, I think that's all I wanted to show there. Let's just run it. I don't think there's a whole bunch to see other than the fact that we'll do it anyway. Helm install dev node, no, it's not node selector, node affinity. I think the hardest part to me about that is just the density and indentation of the syntax. It's just a lot of indentation and hard to keep track of what level you're at. So kube control get all. And you can clearly see it's creating, so that's good. At least it's scheduled. So then kube control, describe, node example. I don't think we're going to see anything here that's pod. Yeah, I mean, there's not a whole bunch going on here because you just all you really see in your logs is that, hey, successfully scheduled to this node. It doesn't tell you, all the logic it used to get there, but that's how you can see that. And if I look at the events, I believe it's at the top. No. Well, it's got to be here somewhere. Here it is right here. No, minutes. There it is, scheduled. Okay, whew. This is kind of just noisy. So 53 seconds ago, I can see it got scheduled, right? Okay, so nothing really terribly new to see here. So control, and I'm not right now. I'm not sure there's any deeper way to find out the logic underneath the hood of what it did, other than that it successfully scheduled. Okay, so kube control, no, helm uninstall dev. Okay, so let's see. Oh, okay. So looking at this here, okay, so there's a couple like things about this. You notice this in operator here, right here. So that's only one of multiple operators you can use in your logic here. So the more complete set is you got in, not in, does the label exist, does the label not exist, and then you can do greater than or less than. So what's interesting here in particular is the not in and does not exist. And if you think about it, that allows you to do anti-affinities, right? You want to, if you say, for example, if I reverse this, so was it in, not in? If I said not in here, right, this would then turn around and say, give me any node except for 1B, right? So this would essentially cause the scheduler to avoid a particular node. In this case, this wouldn't work so well because then the EBS volume probably wouldn't map. But so this is how you do anti-infinity in this case, right? You just start using different operators. Okay, so that's that. Now, if you think about this, there's two mechanisms now where we can do selection of node, right? We have node selector, which we did earlier, and then we just did a node affinity. And the question now is, well, what happens if you do both? And the answer is both have to be successful. So you can't, you have to satisfy both the node affinity, node selector, and node affinity before that node is considered valid or feasible. Okay. If you specify multiple node selector terms, okay, give me a second. I'm not sure what I'm reading here. So I'm going to pause for a second and reread it and then make sure it makes sense to me. So I already talked about this, but so what this is getting after here is just written in English. Both of these next two statements have to do with what I said earlier, where I said if you have multiple node selection terms, then it's an or, and if you have multiple expressions, it's an and. So it's an and within the lower indent. All of them have to be successful before then it'll schedule the node. But if you have multiple match expressions, the outermost indentation, then any one of them successful will cause it to be scheduled. Okay, so that's really all those two paragraphs were. Okay, so now I want to switch gears to pod affinity, right? So let me see if I can remember this. So basically, so far we've been looking at labels of nodes, right, to decide whether or not to schedule it. Now we're going to look at labels on pods, and so that's what this whole section's about. Basically, scheduling based on other pods that happen to be running on that node, right? Or maybe a group of nodes. So this is where it gets a little bit confusing. Let's see. Just like before, there's two different flavors. There's required during scheduling, and then there's a preferred during scheduling. Again, first one has to do with the feasibility of it, and preferred is more about weighting among possible choices. And again, as earlier, we're only going to focus on the required one because it gets complicated enough without adding a preferred. Okay, and yeah, so there's a pod, we'll look at this by example, but there's a pod affinity value, right? Before it was under affinity, node affinity, now it's going to be affinity, pod affinity, right? Now what's a little different here is anti-affinity is, there's another label called affinity pod anti-affinity. Is how you handle the anti-version of affinity. That's different than how we handle node, by the way, right? For node affinity, there was just node affinity, And then by using the different clauses, we had these different, I can't even find it, but the expressions, right? By using things like not in or does not exist, we were able to accomplish sort of the anti-version of node affinity. For pods, the way you do it is you actually have a whole different top-level label. And again, that's going to be blah, 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 blah. Pod anti-affinity, right? We're not going to do pod, we're only going to focus now, just so you know, to keep it simple, we're going to focus on required during scheduling and pod affinity, and make sure we understand that. The other bit of complexity with this too is, if you remember, nodes themselves are not namespaced. So when we use labels, we were just talking about labels on nodes that were kind of cluster wide, right? Pods are namespaced, and if we're going to have labels looking at pods, we have to worry about, well, what namespace are those pods are in? And the answer is, by default, all the logic has to do, looks for pods that are in the same namespace as the pod you're trying to schedule. Okay. You can actually supply another value where you now say you can look at pods in other namespaces. But again, for simplicity in this video, I'm going to leave it the default behavior. So all the labels that we're going to see are going to be all in the same, for pods, in the same namespace as my scheduled pod, which is everything right now we're doing is in default. But it's good to know that you have to think about it a little more carefully for pod scheduling, because they have namespaces. Okay? And then the last thing that's super confusing is, we'll look at the example. There's something we're going to see called a topology key. Okay? So the question then, and see if I get this right. Right. So the general idea is, when you're looking for, you're scheduling your pod and you want to look at a group of other pods to decide whether or not to schedule yourself, or where to schedule yourself, right? The question is, well, what other pods are you going to look at? I mean, are you looking at the entire cluster across all nodes, or what are the grouping? What pods are you going to look at? Now, what you can use is okay, so let me get this right. So there are labels on the nodes. So for example, I'll just do this by example. Let's say I wanted to only look at all the pods in the same availability zone that I want, one availability zone. Actually, let me pause the video because I'm getting myself tangled on words here. Give me a second. So hopefully I can do justice to this, because I'm struggling with this myself a little bit. So the general idea here is with topology key, it's going to be, the topology key essentially is a label that is on your your nodes. And so what you do is, by specifying a topology key for these rules, you're creating groups of nodes. So the way the schedule does is it uses this key and identifies all of the nodes that have the same value of their topology key. In that case, it might be, say, the availability zone. It would say, it'll group all the nodes in availability zone A, all the nodes in availability zone B, and then likewise for, say, C, right? So it creates groupings of nodes. Then the rules that you're applying around looking for pods all are on those groupings. So if I have a rule around looking for pods, and when I have a topology key set based on the zone, it's going to look at all the nodes, all the pods running on that group of nodes to make decisions. And then it's going to likewise do that for B and C. So that's how it's going to decide on which nodes are valid, by these groupings of nodes. And then looking at the pods running on those groupings of nodes. So it's a little bit confusing. And I think what I'm going to do is walk through a concrete example, and that will help us understand it better, or hopefully will. So it turns out that if you look under pod affinity, there's a template here. Now, interesting enough, I just said earlier that I was not going to do anti-affinity, and of course the first thing I looked at is I'm actually using anti-affinity because it was an easier use case for me to explain. So the big picture here is I'm running, so let me walk through the whole thing. I'm running deployment here, right? and I have 3 copies of this thing, which is probably Ubuntu, right? And in this case, I want to try to spread these out across availability zones, right? I want to make sure that if availability zone goes down, that one is running, at least, one is running in a different availability zone. Okay, so in my case, I'm actually, if you think about it, I was running 2 nodes. They're both in 2 different availability zones, right? So my goal is to get 1 running on one and 2 running on the other, because there's no place for the third one other than on one of the other ones, right? So I want to spread them out as evenly as possible. That's the kind of the goal with this example here. And the way I achieve this is with an anti-affinity. So let's see if I can walk you through here. So the topology key here is indeed the zone. So if you think about the way the logic goes is when the scheduler hits this, it's going to say, okay, I'm going to take all my nodes and I'm going to group them into, in this case, camps or groupings based on their topology. So in this case, I only have 2 nodes and they're both in different availability zones. So I basically have 2 groupings. I have the nodes that are in availability zone A, which is one of them, and I have the nodes that are in availability zone B, which is still one of them. So, but I have two groups, right? And then what I do is I'm going through, and of course I said earlier I wasn't using preferred, but I'm using preferred too, right? So what I'm doing is I'm giving a weight of 1, and because this is anti-affinity, it's sort of like a negative weight, right? If you get a weight here, it's a bad thing, so it's going to try to avoid that node, right? So in this case, I'm saying if I find, if you look at the labels of this, these pods are all named, have a label called release dev, right? So they say, hey, if there's any other nodes in that grouping of release dev, then give it a weight of 1, in which case it will try to avoid that node, right? So basically this logic here says, it'll look in the first pod gets scheduled, there are no nodes running, so no weight gets applied. So it gets dumped on, there'll be 2 feasible nodes. It'll drop it in, say, the A one. Okay. The next pod that comes along, right, because I'm trying to get 3, it's going to look at both. The first calculation is it's a look at the node A, right? It's going to see that there's a pod running there. This rule will say, hey, give it a weight of 1, right? And then that weight is an anti-affinity, so it says, oh, I should try to avoid that. So it'll then the other feasible node would be the one that's in B, and that has no weight on it because there is no node running there. And boom, it gets a weight. It gets scheduled to B. The third one comes along. This rule will actually trigger a weight of 1 on both of the nodes because both of them have pods scheduled to them. In which case, it's going to pick just randomly between the 2 because both have exactly the same weight. So this is one pattern where you can, this pattern here is like prefer to spread out the nodes across availability zones. And you look at the examples in the docs, there's lots of patterns you can think of here. With other pods, it gets pretty complicated. Like for example, you can use an affinity to say put all the pods on one exact node by using a different topology key, like the host name of the node, in which case you can collate all the pods onto one particular node. Okay, but either way, hopefully this explained this. So to run this, it's not going to be, again, terribly exciting. Cube, Helm, install dev, pod affinity. And all I really will see is, let's see if I have an output here. Let's see. Oh, I do have it. Yeah. I'm going to copy this. So they're all running. Now, it's hard to see what nodes they're running on, so you can do cube control get pod, and then you can use a custom output with custom columns. So I'm doing node, and it looks at node name, the name of the pod. If I run this, I should see, right, so the 2 of these should be the same. The top 2, right, pods are running on, 2 of the pods are running on the same node, and one's running on the third one. The point is they're not all on one, because, right. Now I think out of the box too, I've seen, remember anyway, this is almost the default behavior of Kubernetes, is that it will attempt to spread these things out for you across nodes, but it doesn't have, here's the catch though, it does it across nodes, it doesn't have a concept of availability zones. So this one's a little bit more subtle in the sense that I'm actually spreading it across availability zones, which happen to be the same thing as nodes in this case. But if you had a ton of these nodes, you could imagine that let's say you have 50 nodes, 10 of which are in availability zone A, 10 in B, and 10 in C. The default behavior might put all of your pods all into the nodes, spread across nodes, but all on availability zone A. This way I'm able to tell it to spread it across availability zones. Okay, and which is the whole point of this exercise. So I think, a little bit rambly, I think that was all I wanted to cover in this section. Thank you.